Hey, let's get real here. This week did not go the way I wanted it to. I really wanted to have more. I worked hard, and what do I have to show for it? I have a new circuit, revised, from our previous video. I have simulation results. I have a bunch of components stuck on this breadboard here, but I don't have the signal that I wanted to show you. The sooner we can accept that there are going to be weeks like this, the sooner we can move on and really make progress towards the end goal here, which is to make a synthesizer, learn a lot while we're doing it, and document the process. And this is a real part of the process. So let me give you a quick overview of the circuit, and then I'm going to show you some breadboard tricks. This is our control voltage source, our charging source. What we're going to make is basically a sawtooth wave, but this box here kind of simulates where we would have a control voltage coming in, and we reference it to ground to create a current here, and then we use this mirror to flip it around so that we can actually charge the capacitor through this rectifier switch. On the bottom side, we have a discharge source, and this discharge source is basically going to short that capacitor down. And so I set up a reference that's about minus 10 volts here. So, and I can choose a resistor here that gives me a reasonable amount of current. Basically, we never want more than some amount of current flowing through this transistor because it'll get hot, I guess. So this is the rectifier switch that we talked about, the same sort of oscillation capacitor, and then finally, a comparator that does some hysteresis. Now coming down to this breadboard, these two transistors that are slammed together there, that is the current mirror. And these diodes that are all jammed on top of each other, that there is the rectifier. It's super hard to see how it's set up on the breadboard, but let me draw up on paper the way this works. A rectifier kind of looks like this. We have this array of 4 diodes, right, that are all oriented in the direction to make the current kind of flow this way. So in our circuit, we have the charging current coming in here, and we have a draining current coming out there. And then we hang a capacitor off of one side here, and then we have that square wave signal coming in here, which effectively forces some of these diodes to turn on or off. But how do we plug this efficiently into a breadboard? Well, a breadboard, right, is these sets of 5 pins that are all connected, right, like this. Right, and in each of these holes, each of these squares, essentially, we have these holes where we can plug our components in, right? And we only get 5 of these, so it's important to use this space efficiently. And so the way I've found to do this that works pretty well, you can start anywhere, but let's just start up here. If you put a diode here between those two, and a diode here between those two, my current is kind of always flowing in this direction, so from positive down to negative. And so these diodes here are kind of like this one, maybe 1 and 3. And then this diode here too, right, we can put, well, it's going to go between here and here, right? So we can go through diode 2 to 3 to out, and then of course the other one goes here. And so here we have a very compact way of arranging our components so that we only take up 3 rows. We have 2 sets of holes that we can use for all of our other wiring to connect out to our capacitor. And there's probably some sensing thing over here, right? So there are multiple connections that need to go right there. And this point corresponds to, this is between 2 and 3 is the right edge. And this here between 1 and 4 is the left edge here. Right? And so it's nicely set up so that you have the source and the sink essentially on the extremes, and then these two in the middle are completely symmetrical. Okay, Now we can also set up an efficient way to build a current mirror. And so in a current mirror, the bases are tied together and the emitters are tied together. The emitter is always the one with the arrow on it. I like to think that those both start with vowels, and so the emitter has the arrow and the collector doesn't. Anyway, so on my... Oh, I didn't do that right. On my transistors, the base is in the middle, just like almost every transistor, and the collector is on the left and the emitter is on the right, when the flat side is here. I like to face the flat side towards me on the breadboard because then I can look at the part number more easily. So if I put one of those here, collector, base, emitter, well, the emitters and the bases need to be tied together, so I can just put the other one here, right? Except that this collector here, this one, is also tied to the base. So we don't need to put it there. We can bend the leg around and put it here. So we have one transistor sitting here with its collector, base, emitter, and the other one sitting here with its collector, base, emitter. And then how do we remember which is which? Well, in this first column we have one pin. In this one we have 3 pins connected, and then in this one we have 2, right? And so we have 1, 2, 3 pins. That's this reference. 3. So 3 is going to be our current reference. And the one where there's 1 pin is going to be our current load. And then this pin here is the one that we're going to tie, to VCC. And of course, these here are PNP transistors. You can build this whole thing the other way around so that you have NPN transistors. The way I like to remember NPN versus PNP, if we think about a diode inside is just a PN junction. Conventional current flows from P to N. And if we look at these little diodes that are on our transistor symbols, this would be the P side and that would be the N side. And so I know the middle is N, so it's PNP. So that's what I've got for you this week. Thanks for hanging out. Hopefully I'll get this working soon. And hopefully I can get some good sound coming out of it too.